Okay, all right. Again, so welcome back. So today we'll keep talking about the security topics and some definitions, and we'll introduce public key cryptography, which we haven't gotten to yet from last time. So just as I thought, maybe can keep things live. Do a little bit of review of the different key security topics we discussed last time. So we'll see this quite a bit in the class. So does anybody want to kind of again quickly remind us what's confidentiality, integrity, and availability? Anybody brave enough on Thursday? So what's confidentiality? Uh-huh. Exactly right. So any unauthorized people or unauthorized programs or systems shouldn't be able to access some data or perhaps code. How about integrity? Anybody? So integrity is sort of the opposite, where unauthorized people shouldn't be able to modify the data. And there are many interesting scenarios that even though maybe you're not able to access the data, you can modify it for example, through fault injection. And then availability is about that the information should be accessible by whoever is authorized. So again, we'll be mostly focusing on confidentiality and integrity. Availability is more like a distributed systems topic, or to have availability, you have to have many different systems, because any one system can be just turned off. So usually we don't focus on availability, but we'll talk about confidentiality and integrity. And a lot of these terms focus on unauthorized access or unauthorized individuals. So do you know the kind of remember the access control, authentication, and authorization? Um, Right. So again, so access control basically ensures that only the authenticated users are able to perform the actions they're authorized to do. So you have authentication, which is the mechanism for identifying who the subject is, or who the program is, or a process, and then authorization is the mechanisms that determine kind of what access you have. So you have to have you're authenticated through your password, for example, and then once you logged in, there is some system table that tells you what you're able to do. So again, a lot of the security attacks on quantum systems and classical systems basically try to breach the confidentiality integrity, where somebody who hasn't been authenticated or authorized is able to change the data or access the data. And then we had this important definition of a trusted computing base. So basically, trusted computing base for a computer system is a set of all the software and hardware components that are working together to provide some security features, and it can again be hardware, software, also maybe network protocols, things like that. And there was a interesting distinction between a trusted and a trustworthy component. Do you remember what's the difference between trusted versus trustworthy? Uh-huh.
Trusted was something that you're depending on, and trustworthy is something that's like, I guess, should or can depend on, like not necessarily that you are.
Okay, yeah, exactly. So trusted components, you depend on it for the system to work on correctly, and then trustworthy is something that's been somehow verified or proved that they're really trustworthy. And the key part is that the trusted component, which is part of the trusted computing base, may not be trustworthy. So most of the times we assume the components are trustworthy, but if we get into issues such as supply chain attacks, for example, if somebody can modify the software or the hardware component that you depend on, then it might not be trustworthy. Or if it's something that a library package you download from the internet, it might not be trustworthy. So this is a kind of a small and but important distinction about you depend on something, but it may or may not work correctly. So we also, I think, mentioned insider attacks, for example. So an insider attack might be an example of an untrustworthy person or a component. So, you let's say you have a data center where the quantum computer is located, and you trust that, this thing is secured, but then somebody inside who's responsible for managing the computer and making sure it operates correctly might not be trustworthy, and that there might be the person performing some attacks. So, yeah, so that's kind of an important distinction. And then we also talked about threats, attacks, and vulnerability. So, what's the relation between the threat and attack and vulnerability as well? So threat is basically usually a set of a set of problems that you're doing, and then attack is one instance of that threat. So threat is any action or anything that can be done to manipulate the system or damage the system, and then the attack is a specific instance of the threat. So when we design a security mechanism, you try to protect from different classes of threats, which is in your threat model. But then yeah, and then hopefully all the attacks within that thread are protected. So, and then vulnerability is sort of, what does the attack? So the vulnerability is something that the attack exploits to manipulate the system. So, I think yeah, most of the times, attack and vulnerability are sort of interchangeable. That the attack targets a specific vulnerability. Okay, cool. And then we talked about different types of cryptographic algorithms. So last time we covered symmetric key algorithms and cryptographic hash functions. And so maybe what is some feature of a symmetric key algorithm that we discussed last time? Why is it called symmetric?
You can like reuse the key to encrypt the plain text, and then we can use the same key to decrypt.
Exactly, right. So for symmetric key, you have the same key that you use for encryption and decryption. That's why we call it symmetric key cryptography. And then hash functions are for protection of integrity. So in the hash functions, do you remember any one interesting property of a hash function?
It's just a one-time key, and you can you cannot decrypt it.
Yeah, so it's a one-way function, right? So for a hash function, you have some input, arbitrary size input, and it generates a fixed sized output, and that output is the hash or the fingerprint or the digest of whatever the input is, and then the key feature of cryptographic hash functions is that it's hard to reverse. So given the output, it's hard to figure out what's the input, and then also given given a hash or two hashes, it's hard to find two messages that might be colliding. So we talked about those, and so today we'll talk a little bit about public key ciphers or public key cryptography, which mainly breaks into key exchange and digital signatures. So key exchange or public key cryptography or encryption deals with confidentiality, and then for authentication and integrity, we have digital signatures. Okay, so for public key cryptography, basically in public key cryptography, we have different keys for encryption or signing, and then for decryption and verification. So I guess the public part of the public key cryptography means that there's always one secret key that you keep, and there's another public key that everybody has access to. And the good thing is that this eliminates the need for having a shared secret. So if you're doing AES encryption, for example, like we said, we have to have the same key for encrypting and decrypting. But then how do you get a same key? If one person is in Europe, another person is in Asia, how do you agree on a same key? So this kind of issue is taken care of by public key cryptography. And I'll introduce the two concepts of key exchange and digital signatures. But basically for the encryption, anybody with knowledge of the public encryption key can encrypt a message, and then you can decrypt it with your private key. So you can post your public key on the internet anywhere. People can use that key to encrypt some message that they send to you, and then you can use your private key to decrypt it. So so this kind of again allows anybody to communicate with you securely, and once it's encrypted, everybody else knows the public key, but that's not sufficient to decrypt the message. So once you encrypt something and send it, only the person with the private key can decrypt it. And then for the authentication, it's kind of the opposite. So you sign the message with your private key, and then with the public key that everybody has access to, they can verify that this message came from you. So you have these two sets of keys. And so this is kind of the picture that for the encryption, you have again some plain text. So this is whatever information you're trying to encrypt. Then through your public key cryptographic algorithm, you encrypt it with a public key to get the ciphertext, and then you use on the other end use the private key to decrypt it and get back the original message. And then if you're doing the signatures, then again you take something that you want to sign, then you use a private key with the algorithm to generate the signature. And then given the signature and the public key, you can get back the plain text. So for example, in computer systems, a lot of times use signatures, for example, for firmware. So if you're updating some firmware of the computer, that whoever writes the firmware, the company like Microsoft might sign the firmware, or like they might sign the device drivers. And then you can, when the computer loads the new code, it can use the public key to verify that this is coming from a correct source. So any questions about the public key cryptography at this point? Okay, cool. So I thought this is a good aside to talk a little bit about Shor's algorithm. So one of the main motivations for quantum computers has been the Shor's algorithm that's proposed to basically break a lot of the cryptographic schemes. And then so Shor's algorithm doesn't work against AES or symmetric key algorithms or hash functions. It's so far, it works for public key cryptography where it targets either RSA or ECC. So RSA is a public key encryption algorithm that uses integer factorization. It's based on the hardness of integer factorization problem, and then ECC or ECDSA, which is a specific instance of ECC, is based on the discrete logarithms. So these can, if you have a quantum computer, then Shor's algorithm could be used to either factor the integers or solve the discrete logarithm problem. And then now the thing I want to talk a little bit about is that Shor's algorithm is really great, but it has a number of limitations, mainly in the fact that to actually execute Shor's algorithm, you need to have a quantum computer with noiseless qubits to be able to actually run the circuit. And Shor's algorithm itself is quite big. You need like 2,000 logical qubits and huge number of gates to actually execute it. So it's really good algorithm, but you can't exactly run it on the quantum computers today. So to give you kind of some introduction to RSA and ECC, and then one slide about kind of where Shor's algorithm is with respect to like the machines that are available today. So at a very high level, basically RSA is a family of public key cryptographic systems. They can be used for RSA could be used for both encryption or digital signatures, as we saw before. You basically use whether you how you use the private and public key sort of determines if it's a signature or a encryption algorithm. And the main property that the RSA leverages is that in RSA the keys are basically related to two prime numbers. So this is not the whole part of RSA, but the key part of the RSA is that you basically have two primes, P and Q, you probably heard about, and then whoever wants to generate a secret key picks P and Q, which are two primes, and then when you multiply them, you get this modules, and then the problem is that given n, it's very hard to factor n into two primes. So if once you generate the key, the P and Q are part of the secret key, and then n is part of the public key. There are other parts to RSA as well, but I think this is like the core part. So if you could factor n, then you basically break RSA. So this is the integer factoring problem. And for RSA, it's actually same with AES. When you see a cryptographic algorithm, it usually has some number associated with it, and typically that number is the key size. So for AES, we saw 128, 192, 256 for the different key sizes. For RSA and in general for public key cryptography, the keys are bigger. So usually you have RSA 2048 or RSA 4096. So these would be the two types of RSA, which we have key of 2000 bits or 4000 bits for the key. So typically so if you have RSA 2048, then each P and Q is of size 1024, and then when you multiply them together, you get the 2048 size. So the bigger, of course, the better. It's harder to break, but it also means that the computation takes much longer to encrypt or decrypt. And so the key, so you have RSA, but then different sizes. If RSA was 128, then you could break it very easily on your on your laptop, but not for huge sizes. So for RSA, it's based on the integer factorization problem, and this n equals PQ, sort of the heart of it. And Shor showed that you can do this factoring much more efficiently on a quantum computer. The other algorithm or set of algorithms is ECC, which is based on elliptic curves and then the discrete logarithm problems. So in ECC, it's a different type of algorithms, and the problem is the difficulty of the elliptic curve discrete logarithm. And then in ECC, the main equation is actually this equation y squared equals x cubed plus ax plus b. So this is the curve. It's called the elliptic curve. There's a curve involved, and then on that curve, the private key is a secret random integer k, while the public key is some generator g, and the point on the curve q. Okay, so what are these things? So in ECC, in elliptic curves, you have a curve. So this is this squiggly line is the curve, and then the curve is public. So there's some standardized curves with A and B being public, so everybody knows what the curve is. And so the curve is this planar curve. So this is the curve, and then elliptic curves have two very interesting properties, which is the point addition and point doubling. So this picture tries to show the point addition and point doubling. So point addition is basically if you have two points, if you have two sets of xy coordinates. So if you want to add these 2 points, you basically draw the line through these 2 points. Then wherever it intersects with the curve, then you flip it over the x, and then this is the result. So if you want to do p plus q, you take the 2 points, you draw the line and you flip it, and then this is the result. So basically all the additions and multiplications end up being as points on the same curve. And then the other operation is the point doubling, which basically, if you have p, you want to find what is 2 times p, and then to find out what 2 times p is, you have your point on the curve, and then you draw a line that's tangential to that point, and then basically kind of similar, you draw a line wherever it intersects with the curve, then you flip it over the axis, and this point is 2p. So for adding any 2 points, or for doing any doubling, you always end up with a result that is a point on that curve. And then so what is this? What is the private and the public part? So the So the public part, actually, should also mention that for the public key, it's called a generator, but it's basically a point. So you have this curve, and there's one point on the curve that's known to everybody. This is sort of like the starting point. So you start at some point. And when you're generating public and private key pair, you start with a known point that everybody knows, and then your private information is this k. So k is usually a very large integer, and then so you start with a known point on the curve. You multiply it by k, and then that gives you another point on the curve. And then this other point on the curve is related to the public key. And then the hardness, the problem is that given the knowledge of the public generator of the initial point, and given the knowledge of the final point, it's hard to figure out what this k is. And this and to realize this multiplication, they use something called add and double and add. So for example, again, when you do this multiplications on like an integer multiplication, you just use these additions and point doubling. So like a example might be like if k is 7, for example. So if k is 7, then you would so you always start with g. So if k is 7, let's say, then you would you start with g, and then you double it. So if you start with g and then you double it once, then you have 2g, and then you add 1, so you double and add. So you doubled it, and then you take this, and again you add it to the original point g. You get a third point, and then that's 2g plus g is 3g. So now you have 3g, and then again once you have 3g, if you double it, then you get 6g, and then if you add one more g to it, you get 7g. So by constantly doing doubling and addition, you can basically multiply a g initial point by any number, and then you end up at some final point that's also on the curve. Long story short, after you do all the doubling and addition, you end up on, there was some starting point, you end up at some final point, and then that's a public key, a public part of the public key, and k is secret. So yeah, there's a lot of cool math that goes inside, but at the high level, I think that's kind of what we want to know, is that without Shor's algorithm, it's hard to kind of, given the final point, figure out what is this large integer k. That's your secret key. One nice thing about ECC compared to RSA is that the key sizes are smaller. So for example, for ECC, a 256-bit ECC key is believed to be as secure as a RSA 3000 or so bits. So a lot of people, ECC has been used for a long time, but the key sizes are much smaller. But then both RSA and ECC have the problem that you have Shor's algorithm. So I will not go into Shor's algorithm, but I just wanted to show some numbers to give you an idea of when quantum computers can break Shor's algorithm and can break encryption using Shor's algorithm. So for Shor's algorithm, I think there are two main issues: that you need sort of these noiseless qubits, and you also need a lot of quantum operations to execute all the gates in the algorithm. So the first thing is that current quantum computers, which we'll discuss a little bit next maybe 2 weeks, we'll start discussing, or next week even, a little bit, we call them NIST machines. They're noisy machines where each gate operation is noisy. So for Shor's algorithm, you need what's called fault-tolerant quantum computers, where the qubits are error corrected, and they're called logical qubits. So if you hear somebody talk about qubits, usually they mean about the physical qubits, and when they talk about logical qubits, that usually means they're talking about a fault-tolerant quantum computer where the qubits are error corrected. So we'll also talk about the error correction a little bit later in the class, but at the very high level, in a fault-tolerant machine, you have one logical qubit is made of many physical qubits, and some sort of a error correction algorithm is used to basically read some of the stabilizer qubits to figure out if there's an error, and then do the error correction. So one of the key parts is that for each logical qubit requires about 100 to 1,000 physical qubits. So people are always improving these numbers, but when you hear about a logical qubit, you can think of it, okay, that needs about about uh, about 100 to 1,000 physical qubits. And then for Shor's algorithm, let's say if you have RSA 1048, then you need about double that. So you need about 4,000 logical qubits. And then so 4,000 logical qubits becomes 400,000 or 4 million physical qubits. So it's a lot of physical qubits that we currently don't have.
So for like real quantum computers today, like I haven't seen like a computer that has more than like 200 physical qubits. So do people actually run error correction at all?
Very good question. Yeah, so there's some machines that are bigger than few hundred qubits, but yeah, for fault-tolerant quantum computers, uh, they're machines with maybe few logical qubits. There's really no, like most of these machines that you can access over the internet from IBM and others, they're still noisy machines. So yeah, so we don't really have a machine that has more than, I don't know, less than 10 logical qubits. That's a good challenge, and good question. But we do have always there's advances, and then actually there's some recent work from even I think even a few days ago. So I took this graph. So this work basically shows for different years how people have optimized Shor's algorithm to how many physical qubits it needs. So let's say in early 2000s you needed like the best estimate is you need like 1 billion physical qubits to run Shor's algorithm, and then these are for RSA or ECC. And then so as years have progressed, people have found ways to improve those needs. So this so then you go from 1 billion to maybe 1 million. So you get into this range of million physical qubits. And then this most recent work, a set of most recent works actually gets the number to, let's say, 100,000 or maybe even 10,000 physical qubits. They assume this non-local connectivity, which we'll also talk about later. So if you have like superconducting qubits, maybe you've seen the picture. Basically, certain qubits are physically connected to only adjacent qubits. So a qubit cannot directly connect to any other random qubit. It's fixed in the topology. But if you have like a neutral atom architecture where you can move around the qubits, any qubit can possibly interact with any other qubit and have this sort of this non-local connectivity. So assuming some, making some assumptions, they're actually getting down to 100,000 or 10,000 physical qubits.
What does it mean by like the cycle times?
Very good question. I'll mention this on next slide. So cycle time basically means how long does it take to perform one physical gate operation. So like we'll talk about like X gate or CNOT gates. Like how long does it take to perform that operation? So in our computer, we're talking about gigahertz, nanoseconds. But for quantum computers, the cycle times are much slower in like megahertz or even kilohertz. So, but this is exactly like you can think of it like like how long it takes to do one instruction. Yeah. Cool. But very good question. And then it actually, any question about this graph? I think the main takeaway is that on the algorithm side, people are you can't exactly run Shor's today, but you're getting closer and closer and closer to to a smaller number of qubits that you would need. And on the other hand, the industry is like 200, 400, or 4,000. The machines are getting bigger. So at some point, the algorithm requirements will be matched by what the hardware offers, and then you can use Shor's in practice. And I haven't read this specific work, but there was some related news that Google and others are pushing to kind of transition away from RSA and ECC even before this end of this decade, because these advances are getting faster and faster. So a question about cycle time, which is a very good question and something that people don't think about it actually too much. When we talk about Shor's algorithm, I think a lot of times, or actually any algorithm, a lot of times the focus is on like how many qubits you need, and we don't have that many qubits. But the other part is that how long does it actually take to execute this thing on a computer? Even if you have enough qubits, how long does it run? So Shor's algorithm is actually a pretty large circuit. So and the estimates again, this is just kind of like an estimate, but let's say the depth of the Shor circuit. So the depth when we talk about quantum circuits, basically um, how deep the circuit is, how many gate operations it has. So the deeper the circuit, it takes longer to execute. And then so given some key size of bits, so 2048 bits, then n cubed is how many gate operations you are getting into. So this is again, so for n equals to 2048, you need to perform about 8 billion operations, and this is a sequential steps. So assuming the gate operation of like one microsecond, then this will take about 2 hours. If one gate operation is about 1 millisecond, then it will take 99 days. So it will take 3 months to do the factoring. But another thing is that these gate times, when you talk about logical qubits and fault-tolerant quantum computers, the gate times are for the logical qubits, which are built on top of physical qubits. So there's another factor of overhead that the gate time for a physical qubit might be let's say 50 nanoseconds or maybe less, 25. It's on the order of tens of 10 or 20 nanoseconds. So like if you go to like IBM, for example, they tell you some gate times for C0 gate or X gate, and then this is on that order. But then when you build a logical qubit out of physical qubits, the operation of the logical qubit actually requires many gates, and then so the logical gate time becomes like 5 milliseconds. So maybe this is too much, but let's say the logical gate time is somewhere in the low milliseconds. So that means that we're talking about if it's 3 milliseconds, we're talking about 1 year. So it would take 1 year on a few hundred or 100,000 qubits to actually run one instance of a Shor's algorithm to break one key.
Another question I have is about like the coherence times. So won't like the use lose?
Good question. So the benefits or the reason we're going to logical qubits is that you don't have to worry about the decoherence anymore. So what the logical qubits take care of is that the physical gates, they decohere, but through error correction cycle, they decohere a little bit. You measure things, you error correct them, and then you get the original data. So logical qubits are not perfect, but you get away from this problem of decoherence. And now, if you get into 99 days, there's still probably a lot of problems with decoherence, even for logical qubits. But the whole purpose of fault-tolerant quantum computers is to eliminate the noise and make things not decohere as much or much less. So this is kind of not to make Shor's algorithm sound negative, but just to make it more realistic that it will take many qubits to run it for a long time.
I'm just curious, since I'm very new in this field, so what is the percentage of field calculation and error correction since we have so much qubits only for error correction?
I'm
just curious, what is the percentage of field calculation and error correction?
So it's sort of layered. So the error correction runs on one layer. So error correction runs all the time. It's constantly measuring the physical qubits and error correcting them. And then on top of that, you build the logical qubits. So there's no like a split, this much error correction and this much actual computation. It's not like you do some computation and you error correct and then you computation again. It's more like you're always running maybe like in your computer, like the DRAM memory is constantly error correcting itself. There's an error, there's an error correction code that checks the DRAM memory. And then when you're accessing some data from your computer, you don't even care about the error correction because it's on the lower level. So that's the kind of the abstraction. And I found just to coming back to the time for last time here, I found this cool graph from a paper from a few years ago, which actually seems to match what people have been approaching in 2023 and recently. So this basically the graph shows this is the number of qubits and then sorry, number of bits. So this is the size of the RSA. So let's say for 2048 will be at 2000 bits. And then this is the time it takes to factor the number. And then these lines are showing using Shor's algorithm on a quantum computer where this is for different gate times. So like, if we have 1 megahertz or 1 millisecond, then by their estimate for a 2000 bit number, it should take one day. And then the more recent data is okay. So for 1 megahertz, so for 1 microsecond, it should take about 1 day, and then now it's a little better to 2 hours. So it's pretty accurate. And then for 1 kilohertz, for 1 millisecond, again, it gets in 10 years, but it's a little bit less. So I think it's pretty accurate. So it shows you how the size, as the faster you can get the quantum computer, you will get the time much less. And then this line, these two lines are for a number field sieve. So number field sieve is basically a classical method where you try to factor the numbers, and then so see here, if you use a number field sieve with like 100 PCs, this is how much time it would take, and then it's way slower than the quantum computer. So, but just for the reference, this is sort of the best classical you can do, and then this is the best you can do with Shor's for different speeds of the quantum computer. So maybe the takeaway message that Shor's is really great, but for both Shor's algorithm and a lot of other algorithms, you have two limitations of actually how many qubits you need versus what's available today, and then how long does it actually take. And I feel like most people right now are focusing more on the qubits part, and then less people are focusing on how long it takes to execute. But nevertheless, this is the whole reason for quantum computing industry to make things bigger and then faster and kind of get us there. So I also wanted to mention as an aside, Shor's algorithm breaking classical algorithms. So of course, people are trying to find a solution to that. So actually, for quite some time, National Institute of Science of Standards and Technology, NIST, has been running these processes to find new cryptographic algorithms that are not believed to be broken by a quantum computer. And I'll not go into details, but I just want to make sure you're aware of them. And we're not doomed that there's a quantum computer because there's a lot of other algorithms. NIST calls it a process. Some people call it a competition because there's many people who submit algorithms, and of course there's one winner or a few winners. But the goal of this process is to standardize new algorithms that will replace RSA and ECC, and then this is the competition that basically is providing new algorithms, and now companies like Google or Cloudflare are pushing to adopt these algorithms. So you'll probably see this name, post-quantum cryptographic algorithms. So PQC are cryptographic algorithms that people don't know of a way that you could use a quantum computer to break them. There could be a way, we don't know, but at least not today. They're standardized by the government, and then industry is pushing to adopt PQC by 2030. So for example, by 2030, hopefully your web browser or whatever, everything will not be using ECC, but it will be using some of these algorithms. This is just a timeline to show you that it's actually been going on for quite some time. So fortunately, the researchers and government started to think about it way before quantum computers. I think in 2016, as a reference, in 2016, I think was the first year that IBM made a quantum computer available online, and this was a five or seven qubit machine. So or there was not really even a viable quantum computer when people started to think about that we need new algorithms to defend from the quantum computers, and maybe not so important, but anyway, it's a process, it's a competition. So there were like 69 proposals. Their round two was in 2020, and then round three was in 2022. So in 2022, four algorithms were standardized: one for key exchange and three for digital signatures. MLK, Chem, has nothing to do with machine learning, and people are very, why did NIST use ML in the name? But anyway, MLChem is a lattice-based scheme for key encapsulation, and then there are three digital signature schemes, and then last year HQC was standardized. So as a result of the competition, now there are five algorithms that are standardized, and again, your browser and whatever you're using will hopefully be using MLChem and or PQChem very soon, if not already. I think a lot of software companies are already, especially for Kyber, it's implemented. And a lot of times there's the things like Kyber or HQC are sort of the names that were given to the algorithms when they were submitted to standardization, and then the formal name is something a little bit more boring. Like like Ketchak was the proposal for the hash algorithm, and it's standardized as SHA-3 that we mentioned last time. So there's always, so anyway, just fun names people give to things. And then another thing that has happened is a lot of these algorithms in the competition were based on lattice-based cryptography, and as a way to diversify, to promote more algorithms, there's another competition or process that's running in parallel for digital signature schemes. So it started 3 years ago, round two with 14 candidates, 24, and now it's still ongoing. So there's a lot of algorithms that people are working on. None of them should be breakable by quantum computer, but maybe there's some mathematicians or some of you might find a cool way to break them. So it's kind of like more algorithms to create diversity to protect from quantum computers. So when we talk about later, again, security of quantum computing systems for all the classical digital parts, it's sort of implied that these, you wouldn't use RSA to secure the network connection between you and a quantum computer. You'd always use these post-quantum cryptographic algorithms to secure any classical data. And I don't know, any questions or thoughts? I think I like the performance questions, right? The cycle counts is okay, really cool. All right, so just a few more, just a small number of slides to talk a little bit about key encapsulation and digital signatures. I'm not going to go into the details, but just show some pictures of the way that the process works. And then so we have two main, again, subdivisions. There's key encapsulation mechanism and digital signatures. So again, for public key encryption or key encapsulation, again, there's no shared secret. You have two different keys. You can encrypt with the public key and then decrypt with the private key. And then this is the picture for both public key encryption and key encapsulation. And now I'll explain the difference between encryption and key encapsulation, but they follow the same pattern. And so this is kind of as much detail as we'll go into. If you haven't taken a security class, there's always an Alice and Bob. So there's Alice and Bob who are communicating. They usually have a friend called Charlie. There's an Eve who's an eavesdropper. Mallory is a malicious actor. So there's a standard set of friends in cryptography. But given Alice and Bob, if we want to protect confidentiality with key encapsulation mechanism, we have Alice, who generates her public and secret key, or public and private key. So for each for each algorithm like RSA or ECC, there's a routine that's called key generation for generating these keys. So for example, for RSA, picking the primes would be the key generation subroutine, or for ECC, picking the large integer k and doing all the point doubling and addition would be part of the key generation subroutine. So usually what happens is you take a seed, a truly random number, like from the random number generator in your computer, or some other truly random source, and then from that you use the key generation algorithm to generate the public and the secret key, and then Alice shares the public key with Charlie, and you can directly share the key, or you can use like a certificates and certificate authority to share the key. So there are different ways, but if Alice directly sends the public key to Charlie, there's sort of like a chicken and egg problem. How does Charlie know that this is actually key from Alice, and Eve is not sitting in the middle and sending her key? So assuming Charlie knows this is a correct public key, then basically Charlie wants to generate what's called an encapsulated key. So that key exchange or key encapsulation, the goal is to exchange a cryptographic key, which then will be itself used with a symmetric key algorithm. So you have again, given the public key and actually some randomness, you generate a encapsulated key and a ciphertext. And so the ciphertext is basically the encrypted version of that key. And then now Charlie can send the ciphertext to Alice, and then Alice has a corresponding decapsulation routine. It will be different for RSA, it will be different for ECC, where given her secret key and the ciphertext she received, she can decapsulate, get the decapsulated key. So if you remember in that initial picture, you have a public key, you encrypt something, you send the ciphertext, and you have a private key, and then you decrypt. And now, why do we share a key instead of an actual message, or what do we want to send? So the main reason is that RSA is, let's say, like 10 times slower than AES. So if you're doing some encryption, doing public key encryption is going to be 10 times slower than doing symmetric key encryption. So if you're encrypting, if you're Netflix and you're streaming a movie, you don't want to be encrypting the data with RSA. You want to be encrypting the fastest method that you can, which, for example, AES. So for key encapsulation, the idea is that once you agree on a shared encapsulated key, then you have a shared key, and then you can use AES security. So it's like a two-step process. You do the public key operations to get a shared key, and then you actually encrypt the data with that shared key. If you just did public key cryptography just to send a message, you could just encrypt some message with the public key, and Alice could get that message, which would work just fine. But if you have a lot of data, then this is kind of the main method, the main way of using it. So any questions about the picture? So again, so that AES, it's not affected by Shor's algorithm, so we'll keep it as it is. But in the future, all these key generation, encapsulation, decapsulation should be for Kyber or one of these other algorithms. And we'll see this picture all the time. So again, if we want to use public key cryptography for doing protection of data, then again, it can be applied to any digital data. So if you have a quantum computing system, whatever you send over the network or between the user and the cloud provider can be encrypted. Again, you use public key cryptography to get the shared key, and then the network traffic might be encrypted, or maybe even all the way to the quantum computer controller. But again, whenever you're doing some computation or you're dealing with the qubits or the analog signals, you cannot apply this. So this is the same picture that we've seen before. Okay, so for the last part, integrity and digital signatures. So again, so for digital signatures, again, since public key cryptography, we have two keys. Now we have anybody who has the knowledge of a public key can verify something that was signed by a private key. So so now we have the plain text, we have the signature, and then you have a public key, and you can recover the information. Typically, what actually happens is you take your whatever you're trying to sign, you create a cryptographic hash of that, and then you sign the cryptographic hash to keep the signature size smaller. So you wouldn't be signing the whole thing, but just a hash of that thing. And then again, we have Charlie, Alice and Bob. And then yeah, so Bob, when he has a digital signature algorithm, you can use RSA or ECC or others. Again, you have some key generation routine where you generate the public and private keys, and then you take a message, you sign it with your secret key, and then you send the signature and the message to Alice, and then she can verify, given the message and the signature, she can verify if it's correct. If you send a message and a plain hash of the message, then anybody can recompute the hash, and that doesn't work. If you send a message and a keyed hash, or the HMAC that includes the message and the key when you're doing hashing, that works, but Alice and Bob have to pre-agree on the key. So the most flexible way is to use digital signatures where there's nothing shared. It's just a private and public key pairs. So this works great. But again, they have to agree on each other's, or at least Alice has to know that this public key really belongs to Bob. So just as an aside, but you probably heard the name about certificate authorities or certificates, or sometimes there's something in the news that some certificate is revoked, or I don't know, something doesn't work because a certificate expired. So basically, the key thing here is that when you have lots of public keys you want to keep track of, or you talk to a lot of people, it's not efficient to get those from the people directly. So instead, there are different what's called certificate authorities, or basically either companies or systems where you have some central authority, somebody that you trust, let's say Microsoft, Google, or somebody, and then that so Alice and Bob trust some authority, and they have the public key for that authority. So your computer, for example, comes pre-installed with the keys for Microsoft, and then if you trust that authority and you already have their public key, then the authority can distribute what's called certificates. So the authority, let's say, gets Bob's authority gets Bob's public key. They somehow verify that it's Bob. Maybe Bob shows them their driver's license or something, and then so once the authority knows they have the correct key for Bob, then they digitally sign it with the authority's public key, and then they send it out. And then when you receive a certificate, you can say, okay, this is a certificate from Microsoft. You can verify that it came from Microsoft because you have the Microsoft's key, and then the contents of the certificate is the public key for Bob. So now from the certificate authority, you can get the key instead of talking to you. So you might never talk to Bob, have never seen them before, but you can get their information from the authority. And this is not just for people, for signing software, things like that. And yeah, this is kind of the picture, the authority, you trust the authority, and then maybe there's some intermediate certificates, and then finally the certificates for the different keys. So it's more of just like a practical solution to a problem of how do you really know that this public key is Bob's? Because if somebody can trick you, then they can sign messages, or again, for encryption, again, how do you verify the public key is for Alice? So okay, and then so assuming everything works, then you can use the digital signatures for integrity or authentication. And last time we'll see this picture again. Whenever you have some digital information, you can use you can protect it. And the same question remains about the qubits, the control signals, maybe parts of the controller, whatever is not digital. How do you deal with it, or whatever is not static data but a running program. Okay, yeah. So I think yeah. So this kind of, as much as I want to talk about kind of some of the security topics and then cryptography. So yeah, so as a wrap up, we introduced a public key cryptography with key encapsulation mechanisms and digital signatures. Maybe I talked too much about RSA and Shor's and some of the requirements that Shor's has and how long it would take to actually break the algorithms. And then the examples of the key exchange and digital signatures. So next week, we'll kind of switch more into quantum computing topics. So to introduce some of the thread models for quantum computers. I'll introduce topics in quantum computing, but I think most importantly, on Tuesday, we'll start to discuss about the project topic. So you can think about the project and kind of, so I think the main thing next week will be starting the project discussion. Okay, so yeah, let me stop recording and that's it. So yeah, if you have any questions, if not, yeah.
I guess not related to like security necessarily, but just out of curiosity, are you partial to any like qubit platform that you think is like best?
I don't know enough to be partial to any of them. I think I in general, I think most companies are focusing on superconducting qubits because it's something you can manufacture using regular CMOS technology. They're familiar with it. But I think a lot of people also think that in like neutral atom architectures where you have this better connectivity might be good. Trapped ions are much better decoherence time. So I I wouldn't be surprised if a non-superconducting architecture wins out in the end. Maybe that's the way. There's very, I don't have any proof, but I feel like there's a lot of investment in superconducting. Maybe IBM is famous, things like that, but that might not be the main architecture. And then there are also different, in the end, you might have a different architecture for computation and for storage. So there's sort of three things. There's the actual computation, there's some qubit storage for a longer time, and then also networking. So like optical qubits, for example, would be pretty promising because it's easy to interconnect. If you have superconducting architecture, then you have to do some sort of transduction to convert from from one type of qubit to optical, send it, convert it back. So um, I know nothing about transduction, so those could be huge problems. So optical qubits have definitely a benefit that it's easy to connect things, move the qubits around. Yeah, superconducting qubits have a benefit that almost anybody knows how to make them. So it's very interesting time. That's it's really hard to say what would win. Uh-huh.
For the quizzes, do we need to know the details on how these cryptography systems work?
Oh no. I think that the quiz is So the quiz will have quiz on Tuesday. It's more like what's confidentiality, what's integrity, it's main topics that we covered, and also encourage students to come to class. So good, yeah. Don't stress about like memorizing how RSA works, but main concept from the class, and from the prior week or from the beginning of the class. Okay, really cool. Okay, yeah. So yeah, we'll end a little bit early today. And then I'll plan to post the projects by the weekend, on Saturday, the latest. So you can please take a look when they're. I'll make an announcement. Take a look. Maybe some of the details will not make sense, but at least like, okay, do I this simulation thing sounds better to me, or maybe if you have some CMOS design experience, maybe that sounds better, or maybe I'm gonna try a remote quantum computer. So just to kind of get an idea. Cool. Okay, all right, thank you. So see you on Tuesday. Thanks for coming, Jeji. Did you arrive yesterday? Or
Yeah.
okay. Um,
I put all the stuff in my office.